So let's get started with a shape that we're all familiar with, which is a rectangle. You're used to seeing this written with length and width, but I'm going to suggest something a little different, which is we'll call these dimensions height and base. And notice the height and the base make a right angle. That's going to be the case on all of our shapes. And the rectangle's area, which you're all familiar with, is just base times height. Now, this of course would work with a square as well, and then the height and the base would be the same value, and you would get just that value squared. Now let's move on to the parallelogram. And the parallelogram also has a height, and it has that height which is perpendicular to the base. So we'll put this as a base here, and of course, in all parallelograms, the two opposite sides are the same. So that's also a base. And what you can see I'm going to do here is I'm going to cut this triangle here that's created by the height coming down from this vertex D, and I'm going to cut it off and then paste it over here. And you can see by doing that, we've created a shape that's got an equal area to the original parallelogram, but now it's easier for us to calculate because it's in the shape of a rectangle. And we already know that this rectangle is base times height. So the area of the parallelogram is also base times height. Now let's move on to a trapezoid. So here we have our trapezoid. And again, this trapezoid has a height, but this time it's got two bases of different lengths. It's got base 1 and base 2. And what I've done here is I've drawn exactly the same trapezoid except for flipped over and translated. So I rotated it 180 degrees and then I translated it over to the right and glued it on there. And so this is now a base 2 and this is a base 1 down here. And what you can see is we've actually created here a parallelogram. So that means that our area here will be equal to the base 1 plus base 2, because that's now the new length of the base of the parallelogram, times the height. But you can see that in order to do that, I had to create a second trapezoid. So what we'll do is we'll just cut that second one off at the end here. And we'll say that our final area for this trapezoid is really 1/2 of the parallelogram's area. The next shape we're going to look at is a kite. And as you recall, a kite has the property that two adjacent sides are the same, and so are the other two set of adjacent sides. So that is our kite, and we have this other property of a kite, which is that the diagonals are perpendicular to one another. So what we can do is we can imagine this kite sitting inside of a rectangle whose height is the length of diagonal 1 and whose base has a length of diagonal 2. And so that big rectangle has an area of D1 times D2. But each one of these little mini rectangles here, we're going to cut half of it away. So overall, what that means is our area of our kite is going to be 1/2 of the area of this bigger rectangle. So the area of the kite is 1/2 D1, D2. Let's move along to the rhombus. The rhombus, remember, is a special type of kite because it's got one set of adjacent sides that are congruent, consecutive sides that are congruent, and another set of adjacent sides that are congruent, and it just happens that all 4 sides are congruent. And so we can consider this rhombus really a special kite. So that's what this first version is. This is a special kite. And so the area here will again be 1/2 the product of the diagonals, d1 times d2. Alternately, the rhombus can be considered a parallelogram. It's a special parallelogram. It's a special parallelogram. And so it has a height. Again, notice this is not a diagonal because it doesn't go from vertex to vertex, but it goes from vertex perpendicular to the opposite side. So it's got a height, and it's also got a base. And so the area of this rhombus can also be thought of as base times height. Now, which equation should you use? It really depends on what information you're given in the problem. So sometimes it's easier to figure out the length of the diagonals, and sometimes it'll be easier to figure out the height of the parallelogram. So the height of the rhombus. So we can think of it both ways. By the way, a square is a special type of rhombus. So a square, you could also find the area using 1/2 d1 d2. That might come in useful sometimes. And now we're going to look at triangles. And there's really 2 types of triangles. There's right triangles. Right triangles. And for a right triangle, what we have here is the height is one leg and the base is another. And again, notice they make that right angle. So that's how we know that they are the height and the base. So, and we can see that this right triangle makes up half of a rectangle. So I'm just going to shade that part that we're not counting. So we're going to do base times height. And again, we'll do 1/2 of that because we're doing 1/2 of the rectangle. And then we can have a non-right triangle. So any other triangle that's not a right triangle, we can look at. So for a non-right triangle, what we can do is we can draw the height from any vertex. So here we've got a height drawn from C. It's perpendicular to the other side, so that becomes the height, and this becomes the base. And again, what you can see is we've created 2 rectangles, one over here and one over here. And again, we're going to delete half of each little rectangle. So half of this rectangle goes away, half of that rectangle goes away. Because what we've done here is we've made 2 right triangles. One right triangle there, one right triangle there, and we can just go back to what we know about right triangles. So again, the formula here is going to be 1/2 of the base times the height. Same formula, just 2 different ways of looking at it. The final shape that we're going to look at is really a category of shapes, regular polygons. And to recall what a regular polygon is, a regular polygon has all sides congruent and all angles congruent. I'm not going to put the tick mark in this side because it's hard to see, but and all the angles are congruent. So those angles are all congruent. And again, I guess I can do it down here. Okay, so all the sides are congruent and all the angles are congruent in a regular polygon. This just happens to be an octagon, 1, 2, 3, 4, 5, 6, 7, 8. But what we're about to say works for any regular polygon. What you can see here is that I've drawn in a triangle here. And that triangle is an isosceles triangle that's made up by the radius of the polygon. And the height of this triangle gets a special name. it's called the apothem. It's called the apothem, but we really consider it, we can really think about it as the height of that triangle. And so if I want to find the area of just this triangle, what I would do is I would say, okay, the area of this triangle, it's got a base here. And instead of calling this a base, we'll call this a side. So we'll call this a side. And we'll use the letter S for side. But really what it is that's the base of the triangle, but it's also a side length of the regular polygon. And the apothem here is the height, and we'll call that letter A for apothem. So what we're going to say here is that little triangle here, this little triangle, has an area that's equal to 1/2 of its base, which is a side length, times the height, which is the apothem. So it's 1/2 SA, but you can really think about this as 1/2 BH. Same formula, just with different letters. And then what we have to think about is how many polygons, or how many of those triangles we have in a regular polygon. In this case, we have 8, but in general, what we're going to have is we are going to have n of those because we're going to have n sides. So this regular polygon has n sides. It's got n sides. So the regular polygon's area is n times 1/2 of SA. And doing a little rearranging here, what we can say is, let's pull the 1/2 out in front. And then we're going to move the n next to the s. 1/2 n times s, and then times a. Why did I want to do that? Well, if I've got s as the side length and I've got n of those sides, then what this is going to neatly wrap up into is 1/2 of the perimeter, we'll call that P, times the apothem. And I'll write that out in words right below here. So that's going to be 1/2 perimeter times apothem. Times apothem. That's a nice, tidy little theorem there. 1/2 PA. All right, so go ahead and review these. Make sure that you know them all and you are ready to use them. I will say that when you are finding the area of a regular polygon, oftentimes, because we have a right triangle in here, this apothem is a right triangle, we're going to need to use trigonometry in order to figure out some of the variables. So either the apothem or the side length, we're going to need to use some trigonometry to figure out those lengths. And you know how to do that with SOHCAHTOA.